Hello guys, welcome. So today I'll be talking about one paper where Frank Glorius group has published the de-aromatized cascade photocatalysis. It's a part of the photocatalysis, and the this work actually describes the de-aromatization of the starting material, and they have achieved a very special and funky molecules containing cyclobutane fused rings. So again, this work has been done by Frank Glorius. He is a professor in WWU Munster in Germany, and here is a natural frameworks where this type of system this cyclobutane containing fused molecules are present in the natural products and the drug molecules. So Elikanen or Italicine or Gadiltone has such type of moieties, and that has been presented in the paper by the group. So what exactly is the work that they have achieved using this energy transfer catalysis? Again, I'm mentioning the word energy transfer catalysis. So they have used these photocatalyst for the selective energy transfer. PC1 is this iridium based photocatalyst, and PC2 or 3 is also an iridium based catalyst, but the change here is the different R substituents. If you have R equals to hydrogen, and then it's a PC2. If you have uh, other group, fluorine or trifluoromethyl group, then that will be a PC3. So these there are a lot of protocols that have been screened, but these two serves best, and showing the precise triplet energy transfer. That's why I have been chosen in this work. Cool. So they have employed this one naphthol derivatives for the selective energy transfer. So here you can see this ENT is the is the photo is being done by the photocatalyst, and what really it does in the beginning state is do the 2 plus 2 cycloaddition, and then another energy transfer catalyst, that is the catalyst turnover. Again, your iridium catalyst is coming back to its initial oxidation state and generate this type of product. So again, the method is quite uh, amenable, and at the end we are achieving a very nice molecular spectrophones. And let's move on to the mechanism, how this mechanism has been proposed. So let's start with this uh, the starting material that they have chosen, that is the naphthol, two naphthol, one naphthol derivatives. So as I already have said that they have used iridium based photocatalyst that is acting as an energy transfer catalysis. So first iridium 3 is oxidizing, uh, not really oxidizing, just that energy transfer, singlet to triplet energy transfer. I hope you are bit aware of the singlet and triplet states, and the energy transfer that has been done by these photocatalysts within these singlet to the triplet energy transfer causes a lot more uh, change in your starting material. So what it is essentially doing here is, because of this energy transfer, this double bond is now formed the radical diradical species, and it undergoes 2 plus 2 cycloaddition with this alkene. These two radicals undergoes 2 plus 2 cycloaddition with this alkene and forms this de-aromatized cyclobutane sort of product. Again, if you're using uh, since you're using the iridium photocatalyst. So in this step, now your triplet energy, uh, triplet energy state of your photocatalyst coming back to the singlet state, and in this process it is transferring some energy which is being utilized by this alkene and forms diradical in the similar fashion as it has already done in the first step. Diradical then undergoes intramolecular ring expansion and follows by the radical diradical trapping, and you end up with this cyclobutane moiety coming in between the two fused rings. Here, the mechanism has been written by the mechanism is quite, you know, what should I say, is something what had been already been proposed a lot many times before. So, uh, it's okay. Here are the steps that have been followed. First step is 2 plus 2 cycle addition, and the yeah, one very important thing. So you remember that I have already discussed that they have used three type of photocatalyst: PC1, PC2, PC3. So what really is happening here is, if you are using PC1, the reaction stops at this point. The reaction stops at this point. But if you are using PC2 or PC3, that means you have substituents over the ligands in the iridium catalyst, then the reaction goes forward and you end up with this sort of final product. Right, so that's what here written is, with one catalyst the styrene undergoes a vinyl cycle. So that means, if you're using PC3, then this sort of product is again participating in the reaction and giving you this sort of final product. But if you have PC2, sorry, if you have a PC2, then reaction doesn't go forward, it stops at this point. And again, yeah, so uh, this mechanism has been well supported by the some physical experiment that they have done, for example Stern-Wollmer quenching experiments. So that has been corroborated by the Stern-Wollmer quenching studies. All right, let's move on to the scope. How many hot type of examples has been shown in the paper? So there are not many. If you see, I have presented four substrates here, for sorry, 4 into 3, 12 scope, right? So not really, well, so they have changed different R substituents over the electron withdrawing groups, methyl and exyl isopropyl, as well as electron, you know, just a second. Different substituents over the electron withdrawing group, as well as R substituents over the ring, has been changed, and they observed good to excellent yield in each cases. So this is all about the this Jack's paper uh, by the Frank Glorius and his team, and it it has elaborated a very good energy transfer catalysis, how merely tuning the photocatalyst uh, can lead you to the different products, right? So the selectivity of the photocatalyst in the reaction is something what was really very well shown in the paper. And I guess that's all for today. Thank you for being with us. See you guys in the next video. Thank you.